Hello, in this video we're going to have a brief discussion of quantum mechanics. So first off, why do we need to talk about quantum mechanics? Well, it leads us to the conclusion that all energy exists and is transmitted in discrete little packets of energy and not a continuous variable amount. And that one conclusion is the underlayment of a large amount of science that you wind up doing. So we need to talk about this. Okay, so first of all, what the heck is quantum mechanics? Well, alright, so the universe is explained by physics. Classical or Newtonian mechanics explains the world we observe, kinetic energy, gravity, potential energy, things like that. The apple falls on Newton's head, that's Newtonian mechanics. Alright, well, classical mechanics, Newtonian mechanics, breaks down as objects get really small. So electrons, protons, atoms, and molecules do not obey classical mechanics. Classical mechanics also breaks down as you start to go really fast, so relativity is another area where quantum mechanics breaks down. Is there a connection between relativity and electrons and Newtonian mechanics? Maybe. String theory might lead us to that. Who knows? At the moment we just think of them as separate models for different situations, and then the models will all blend into each other when you take quantum mechanics really large, or you take relativity really slow, things like that. Okay, so a little interesting history lesson that leads us to some useful outcomes of quantum mechanics. How do we realize that classical mechanics didn't have it all right? So there were several scientific mysteries from the 1800s. Aside from these, people thought, yeah, physics, we pretty much have that wrapped up. No need to go study physics because we know it all already. And then they were wrong. Okay, so what were the little things they needed to tie up? All right, so classical mechanics mystery number one, the emission spectra of atoms. So the background here is if you take white light, which is light from the sun or light from an incandescent light bulb, and shine it through a little slit here on the left, run it through a prism, you get a spectrum, all the colors. All the colors you see in a rainbow too, because in a rainbow the water droplets are acting like a prism. Water droplets in the air. Okay, but if you take some hydrogen gas and put it between a couple electrodes and put a pretty high voltage across it, you get light out of it. You look at this, it looks kind of red, great, and you pass it through some slits and then through a prism, and instead of getting maybe a band of colors around the red, you get these very discrete wavelengths that are always the same wavelength of light that comes out of this. What the heck? Up to this point, every thing they'd ever looked at through a prism had this continuous spectrum of light, except for gas discharge lamps. So there's got to be a reason why, and they didn't know the reason why. Another picture of this, so the x-axis of all these little black boxes is wavelength in nanometers, and it shows that different elements have different sets of wavelengths too. That, at the time, didn't make any sense. So in 1885, Balmer and Rydberg found an empirical solution that described the hydrogen emission spectrum. And, well, in order to make the math make sense, alright, well, they have their constant here, inverse wavelength is here, and then they have 1 over n squared, some integers going on in here. But why would you describe a gas discharge lamp with integers? It didn't make any sense at the time. We'll talk about exactly why this works in section 4.9 coming up. But, so this is at least an empirical solution to the problem. So empirical means, well, the math works out, but they don't know why it works. Alright, classical mechanics mystery number two, Blackbody radiation. So when you heat a solid, they emit electromagnetic radiation over a wide range of wavelengths. And so you notice this if you get a piece of metal really hot, it starts glowing red. If you get it hotter, it'll glow kind of yellow. And if you get it extremely hot, then it glows white. This is true in your incandescent light bulbs as well. You get the filament inside the bulb really hot, and it glows kind of yellowish white. Alright, but the math behind this didn't work out. And I'm going to ignore how this and why this actually works, but just kind of get to the conclusion here. Classical physics would predict that as you decrease the wavelength, you get kind of infinite radiation emitted, whereas that's not what they actually saw. They saw these kind of bands, and then this will shift a little bit as you change the temperature of whatever it is that's glowing. So again, they didn't know why this works. Alright, so Planck solved this in 1900 by realizing that energy is not continuous, but it's quantized. So that means the energy from the glowing piece of metal could be emitted, or I guess not really absorbed in this case, but emitted in discrete units only. So little pieces of energy and not a continuous spectrum of energy. And so our modern understanding of this is that the frequency of light is related by a constant to the energy that's being emitted at the time. So again, energy is always emitted in integer multiples of the frequency times Planck's constant. Now, Planck's constant, it's really small, 10 to the negative 34th, which is a super small number. So that means it's a really, really small packet of energy that's released or absorbed, but it is still quantized. Let me take a break and say, what do we mean by quantized? So this means it's in little quanta, which is, it just means individual pieces. So if you have something that's continuous, it means you can have 1, 1.1, 1.1111, 1.10. You can have any number you want, only limited by how many decimal places you want to put out there. That's a continuous spectrum or a continuous number. If you have something that's discrete or quantized, it means it can be 1, it can be 2, but it can't be anywhere in between. So that's what we mean by quantized. Okay, at the time that Planck came up with this, he thought this was just a math trick to make it work, and really they'd find some better theory that would make this go away, but it turns out he stumbled on an important fundamental insight about how energy works. Alright, mystery number 3 is the photoelectric effect. And in this effect, electrons are ejected from the surface of certain metals that are exposed to light that has some minimum frequency. So a lower frequency of light doesn't eject the electrons, a higher frequency of light does. And oddly, the number of electrons that get ejected and then collected on the yellow pole here in the diagram, the number of electrons that are ejected is proportional to the light intensity, but the energy of those electrons is not proportional to intensity. I mean, it might make sense that if you shine brighter light on this, you'd get more energetic electrons, but no, you just get more of them. And so this effect cannot be explained by thinking of light as waves, but it can be explained if a beam of light is really a stream of particles. We call these particles photons. And it turns out that the energy of a photon, E, is equal to h, Planck's constant, times nu, the frequency. And since the relationship exists between frequency and the speed of light and wavelength, you can say that energy is equal to hc over lambda as well, and that works out just fine. Okay, so how the photoelectric effect makes sense given this information is that a photon of sufficiently high energy, so a high enough E, which means a high enough frequency, is required to eject an electron from the metal surface. There's something called a work function that you have to overcome that amount of energy in order to eject the electron. And then once you do, well, more light intensity really just means more photons. So you just get more electrons that come off. Now if you change the frequency of the light that you're shining on this metal, well then you get a different energy of the electrons that are released. And it's obvious that I need to buy the full version of this software. Okay. So why do we talk about the photoelectric effect? Well, it was used in some early electronics, early video cameras, the little devices that go across a storefront doorway that make noise when you walk through it. These days we use charge-coupled devices, CCDs, for detecting light, and not the photoelectric effect of certain metals. But hey, this represents a turning point in our understanding of the world. And so the big takeaway here is that light, is it made of particles or waves? And well, this was a big debate ever since ancient times of what light consisted of. And the answer is that it's both. Sometimes you look at light in a certain way and it appears to you like it's a wave. Sometimes you do an experiment, light looks like it's a particle. Light doesn't care what we think. It is its own thing. And then sometimes us humans put our models on it and light fits into the wave model. Sometimes it fits into the particle model. But really light is its own thing that we have no macroscopic relation to in our physical world. Okay, your book has calculations for the photoelectric effect, and I skipped those in my class because I don't really see a point. Okay, so our little spin through quantum mechanics, we have some conclusions that are the really important outcomes here. So on a very small scale, energy is present as discrete quanta. Oops, typo. In other words, energy is not continuous. So you can have certain values of energy, and sure, the difference between these certain values is really, really small, but they're still discrete values. So some examples of this is that electrons around the atom can only occupy certain energies, and this affects how atoms and molecules absorb or emit light. And we talk about this a lot in Gen Chem here. Some other examples, not so much in Gen Chem, but anyways. But so the big ticket here, okay, on a small scale, energy is discrete quanta. Light is transferred in discrete particles called photons, and each photon has a certain frequency, wavelength, and energy. And then also, light behaves as both a particle and a wave, depending on how you look at it. Okay, so something very important. Energy, frequency, and wavelength are all simply different ways to describe the same photon, and you can write relationships between them, which are shown on the slide here. This font doesn't do a good job of rendering the nu, but hey, it's nu, not a V. Anyways, there's different ways to describe the same photon. You can interconvert from one to the other depending on what you are trying to do. Okay, and that's what we have for our quantum mechanics video. Thank you for listening.